Hi everyone. So I'll be talking about electronics circuits, and it's a very easy subject. Don't make up your mind that it is a difficult subject or something like that. I'll be talking about the tricks and the uh, like the implementation I used to use when I had this subject. So let's go on electroniccircuits.aishajita.com, and I will be uploading some videos, and along with that I'll be definitely posting questions, not necessarily that it will be coming in your exams, but yes, practice. So what I want is just practice, practice, practice. Watch the video, pause it, replay it. Another important thing is that what I know want you to know is the basics of electric circuits. You should be thorough with the Thevenin's Norton superposition theorems because they will be using in later units. Another thing, even if you are not thorough with the topics, or maybe you have taken as a new subject out of interest, definitely at some point of time I will upload these theorems as well. And you should be thorough at least with mesh and nodal analysis, which will you might have studied in basic electrical. And I hope you are aware of potential divider and current divider rules, because it is a very, very, very important concept. So let's start with the unit 1. Your unit 1 will have your biasing circuits and small signal analysis. So let's start with the uh, subject. So the unit 1 has your biasing circuits. So the topics are your DC biasing load line, and the bias point, BJT biasing circuits, FET biasing circuits. So what do you understand about biasing? Before reasoning out the needs of biasing, you should understand the meaning of biasing. So, in order to operate a transistor in a desired region, so you already, I hope you know, there are three regions: the cutoff region, the saturation region, and the active region. So, for the transistor to operate in a particular region, we have to apply external DC voltages of current of correct polarity and magnitude to the two junctions of the transistor, and this is called biasing. So your biasing is also known as your DC biasing, or your DC operating point, and or your Q point or quiescent point. So by understanding that, since we are talking about the operating point, which is always in the active region, such circuits are called biasing circuits. That is the circuits that is used to get the desired and proper operating point. The process of giving proper supply to the supply voltages and resistance in the circuit should be suitably chosen. So this is your biasing circuits. Now I will talk about why do we need biasing. So these are the key points. Why do you need biasing? The process of giving proper supply voltage and resistances in the circuit must be suitably chosen. It establishes a Q point to operate in the positive region of the transistor, which is the active region, and for your free distortion free output in the amplifier circuit. So this is the reason. Another things will, there are a few more definitions, like your stability factor, which is an important. I think they might give you in a short question in your paper. So the question here is that how do we ultimately get the amplification of this power which we have achieved as the output? The simple reason is that the DC output, the DC biasing which we are applying at the input of the transistor is less than the output signal. Hence, we need a biasing to be done, because we need an amplification of the circuit. And in any case, we'll be talking about the amplifiers in the later uh, lectures. So now we'll be moving on to your DC load line, which might be a big, you might get in a big question, or maybe in a small, you might get in a small question as well. So let's start with your DC load line. Another more important thing is that each unit is divided into, I don't know, I think the last one is not divided into two, but probably each unit is divided into two sections, your biasing circuits and your small signal model. So important thing is that either if you're comfortable with biasing circuits, or you're comfortable with small signal analysis, go either of the two. In case you cannot handle the pressure in your and this will be applicable only for your semesters, not for your midterms or your cycle tests or something like that. So we'll start with your DC load line. Okay, so the DC load line is a straight line which is drawn on the transistor for output characteristics. So now let us draw a DC load line. So here is your uh, the graph, and you know that this is your active region, this is your active region, and okay, and this is your saturation region, and this is your cutoff region. Active. I'm sorry about the handwriting because this is little bit difficult for me as well. Okay, so talking about the active region, what we see is that we'll be getting a straight line like this, and somewhere in the middle we'll be getting your Q point. This will be your Q point. So what you will be doing is that you will be putting one parameter to 0. Supposingly, okay, we'll not be taking right now voltage or current, we'll be just taking x and y to just simplify the problem. So if you'll be putting y to 0, you'll be getting the value of x, sorry, y to 0, you'll be getting the value of x. And similarly, when you'll be putting your x to be 0, you'll be getting the value of y. Hence, whatever value you'll be getting of x and y, you'll get the Q point. So this is how you form a DC load line. Okay, now let us draw your in terms of your voltage and current. So taking your common emitter configuration, and mostly we'll be taking common emitter. Yes, there will be I'll be teaching common base and common collector as well, but more focus I'll be doing on common collector. So here will be your IC, and here will be your VCE, sorry, and I'll be drawing the voltages. Okay. Okay, this is just a rough drawing. Uh, I hope you will be able to draw a little neatly than me right now, because it's just a rough drawing. Okay, this is your cutoff region. Okay, so now you know that you have your IB here, and here, and here, and here. Okay, so now when you put your IC equal to 0, you will be getting the value of VCE equal to VCC. We'll be solving a question and you'll understand what I mean. I mean how I mean VCE equal to VCC, and your IC Okay, so now when you put your VCE equal to 0, you'll get the value of IC. So your I, and then when you draw the line, you'll get somewhere in the middle your Q point. So I hope you understand what you mean by Q point. So Q point is nothing but you draw a straight line, and the middle point of that straight line is your Q point. So I'll start the numericals based on this DC load line. Okay, so here's a question. Determine the Q point of the following circuit. So this is the circuit, and in other lectures I'll be telling you how to make, because you'll be definitely doing the analysis as well as the design of the circuit. So you need not worry about how to find a Q point. You need not worry about how to design the circuit and all. The circuit will be given, or even if the circuit is not given, you will be knowing about the resistor values and VCE, VCC, and RB, and VB. Remember always that VBE is 0.7. This is the most important thing to remember, because sometimes most of you forget the value of VBE. And even if the circuit is not given, you'll know the formula, and later on when you know how to design the circuit, the you'll be able to manage. So I'll start the how to form a Q point. So okay, so now you have your VCC equal to 8 volts, RC equal to 2k ohm, and RB equal to your 150k ohm. Okay, what you need to find for a Q point is your IC and VCE. These are the two parameters which you need to find. So you need not worry about your IB right now. Okay, to find VCE, we will be looking at this loop, the outer loop, which has, and we'll be using your your mesh analysis. And see, now VCC equal to your RC IC plus VCE. Okay, so now your IC will be going from here. So VCC equal to your ICRC plus VCE. And since your IC for Q point, to find the Q point, we need to put your IC equal to 0 and making this equation 1. So your VCC will be equal to your VCE. VCE. So VCE will be equal to 8 volts. Okay, now we'll be doing your VCC equal to ICRC from equation 1, because making your VCE equal to 0. So you'll get IC is equal to VCC upon RC IC. So IC will be equal to your 8 volts upon your 2k. So you'll get IC equal to IC equal to oh sorry IC equal to your 4 milliamps. Okay, up till here your whole uh, marks distribution, if even if it is a 4 mark question, up till here you'll get only 2 marks, because you'll get another 2 marks for your diagram. So here is your IC in milliamps. Please remember to put the units, and VCE, which is your volts, and we'll directly make a straight line in just we'll not see what are the different voltages or current levels. We'll just see your this, so we'll make this as point A and this as your point B, and here is your Q point, and you will write Q and the value of your VCE. So your value of VCE is 8 comma your uh, current value 4 milliamps, or no need to write 4 because we are putting it as milliamperes, and this because we know this is X and this is Y. When we plot something, we'll put X and Y like this. So this is how you form a Q point. I hope you have understood the concept of biasing circuits and the how to determine a Q point. So in the next lecture, what I'll be talking about is the types of, we'll be moving back to biasing circuits, and we'll be talking about the types of biasing circuits, how to analyze a biasing circuit and to design a biasing circuit. So thank you. So like, subscribe and comment below in case any topic you need me to cover it. Please comment below.